chapter 8 here, acid, base, and salt. Okay, so what we can see here, we have the redox. Redox reaction is one which one species has been oxidized and another species has been reduced. Okay, so what is oxidation? Oxidation is loss of electrons. So example, loss of electron. So let's say I have, okay, so I put an example here, zinc, oxidize to zinc 2 plus 2 electrons. So we say this is an oxidation reaction. So when you say oxidation, you have to use the reactant here, and you mention the reactant, don't mention the product. So you mention that zinc is oxidized. Okay, so that is loss of electrons. As you can see, zinc loses electron and becomes zinc ion. Second point, gain of oxygen. Gain of oxygen is also oxidation. For example, carbon plus oxygen become carbon dioxide. So we say the reactant also, carbon is oxidized. Okay, now the next one, loss of hydrogen. Loss of hydrogen, let's say ammonium change to ammonia plus H plus. Okay, so you can see the hydrogen ions, the hydrogen here change to hydrogen ion. So this is where the ammonium ion is oxidized. So which is the loss of hydrogens. Okay, so reductions, gain of electrons. Gain of electrons, for example, Cu2 plus, get electrons, become Cu. So we always use the reactant and we say Cu2 plus is reduced. Okay, then loss of oxygen. Loss of oxygen, for example, let's say carbon dioxide change to carbon monoxide plus oxygen. Okay, so we balance this 2. Okay, it's balanced. So we say that carbon dioxide lose oxygen. So always say the reactant, carbon dioxide is reduced. So it's reduced. And finally, gain of hydrogen. Gain of hydrogen, for example, NH3, you put in HCl, and then it becomes ammonium chloride. So ammonia gain hydrogen. So this is called reduction. So ammonia is reduced. Okay, so of course there is a special word here, oil-rich. Oil-rich is used to remember the meaning of oxidation. So oxidation is loss of Rig. Oxygen is Rig. Okay, I seldom use oil-rich. Let's look at the websites to see how they remember it. Remembering oxidation by oil-rich. Oxidation involve loss, reduction involve gain of electrons. Okay, it refers to electron, that means this is the meaning of oil-rich. Actually, I seldom use oil-rich also. That's why when I look at this, I don't know. I can't remember. Okay, I can't remember. Oil is Oxidation involve loss of electron. Reduction involve gain of electrons. So they talk about electrons. Okay, so of course we should have one more aspect beside these three, right? So we should have one more aspect that we have to pay attention also, which is the oxidation number. So where oxidation is gain of oxidation number, gain of oxidation number, whereas reduction is decrease in oxidation number. So oxidation number is something like the charge, so 0 to +2. So this is gain in oxidation number. So this is oxidation. This is +2 to 0. So +2 to 0, decrease in oxidation number. So it's reduction. So that is another way. So normally there are 4 aspects. So beside these 3, we have oxidation number also. Now next point, reducing agent are oxidized and oxidizing agent are reduced. So to understand this, let's take a quick example. So let's say I have zinc react with Cu2 plus. This is what we call a displacement reaction. So zinc as a solid put in the copper 2 plus solution, and then zinc displaces copper from its solution. That means zinc will dissolve and then copper will come up from the solution. So this to this is oxidation, and we also know that this to this is reductions. It's reduction. Then after that, what we can say about oxidation agent and reducing agent here is reducing agent are oxidized. So who is oxidized here? Zinc. So zinc is, you see we always use reactant. Zinc is a reducing agent. Reducing agent. So reducing agents reduce copper 2 plus to copper. So its role is to reduce copper 2 plus to copper, so that's why we call it reducing agent. But in order to reduce it, it has to give oxygen to copper, and because of that, the reducing agent lose electrons, lose electrons and become zinc 2 plus. So that's why zinc, in order to reduce copper, zinc has to oxidize. Then oxidizing agent are reduced. The oxidizing agent are reduced. So you see this is copper 2 plus is reduced. So hence copper 2 plus is an oxidizing agent. Next point, potassium iodide is a reducing agent and will go from colorless to red brown. Therefore, it's oxidized to produce I2. I see the equation first. Potassium iodide react with hydrogen peroxide as well as sulfuric acid to form iodine, to form potassium sulfate, to form H2O. We focus on the iodide. So iodide is I negative. I negative. So it's I negative. Potassium iodide, the Ki is I negative. And then it becomes I2. It becomes I2. So basically what happened to iodide to iodine is it is a loss of electrons. Loss of electron. So 2 iodide become I2 plus 2 electron. Loss of electron. So this to this is loss of electron is oxidation. Oxidation. So this is oxidation. Oxidation. Okay, so that's why over here, reducing agent are oxidized. This is oxidized. Potassium iodide is oxidized. So potassium iodide is a reducing agent. Reducing agent. So that's the thing. Potassium iodide is a reducing agent. And we'll go from colorless. Colorless means this one. Potassium iodide is colorless. To red brown. Red brown is iodine. Iodine is red brown. Colorless to red brown. Therefore, it's oxidized to produce I2. I2. Okay. Potassium manganate is an oxidizing agent and will go from purple to colorless. So this one, the equation, MnO4 minus will become Mn2 plus. Okay, so of course this is potassium manganate. This is purple. Then to colorless. Okay, so that is the famous oxidizing agent, potassium manganate. So of course it is oxidized. How you see it's oxidized is not that easy to see from here, but if you see the oxidation number, then you can see this is actually positive 7. That is a way to count the oxidation number, but we don't want to care about that first. You just take it, positive 7. This is positive 2. So positive 7 to positive 2 is decrease in oxidation number. So it is reduced. So something that is reduced is oxidizing agent. So to test for an oxidizing agent, add a reducing agent, which is potassium iodide. And to test for a reducing agent, add an oxidizing agent, potassium manganate. So that means, you want to see whether the chemical is oxidizing agent or not. You add reducing agent to it. If the reducing agent change color from colorless to brown red, colorless to red brown, that means that chemical is an oxidizing agent, because oxidizing agent can react with reducing agent. So the second point here, it means if you have a chemicals, you want to see whether it is reducing agent or not, you add oxidizing agent to it. If the oxidizing agent change color from purple to colorless, that means this chemical is a reducing agent. So that is how we test it. Okay, so up to here, we need to know two examples of it. One example for reducing agents and one example for oxidizing agents. Okay, so the reducing agent is potassium iodide. The oxidizing agent is potassium manganate. So you have to remember these two. Okay, now we look at properties of acids. An acid is a compound which, when dissolved in water, produces hydrogen ions and are described as proton donors, H+. Okay, so for example, we know acid, HCl is an acid. So HCl, you put it in water, then it becomes H plus Cl minus. So HCl donate protons. H plus is known as proton. Okay. So dissolve in water and produce hydrogen ions. Acid turns blue litmus indicator paper red. Okay, so from blue it turns to red. And have pH 1 to 6. Okay, so pH 1 is strong acid, pH 6 is like weak acid already. Okay, so acid plus metal. Acid plus metal is the chemical reactions for acid. Acid plus metal. What kind of metal? Must be reactive metal. Okay, must be reactive metal. Example for reactive metal: potassium, sodium, calcium, magnesium, aluminium, and zinc. So these are reactive metals that can react with acids. So when they react, they will form salt plus hydrogen gas. Okay, so let's see one example. If you have HCl as the acid, you have magnesium as the reactive metal, then they will form salt, right? So the salt is magnesium chloride, MgCl2 plus hydrogen gas, H2. So that is how we understand that equation. So the next reaction is acid plus base becomes salt and water. So example, acid. So base normally they are oxide hydroxide. Okay, oxide hydroxide, or maybe you can also use ammonia as the base. Okay, so let's say I put one example, sodium hydroxide. Sodium hydroxide is a famous base. Sometimes you heard alkaline. So alkaline base is the one that can react with acid. Okay, so they will form salt. They will form salt and HCl plus water, H2O. So that is neutralization. The next one, so this one is neutralization. This reaction is neutralization. Okay, so the next one, acid plus metal carbonate. You get salt, carbon dioxide, and water. So for example, acid, okay, now I use nitric acid, HNO3, nitric acid, plus metal carbonate. Let's say I use calcium carbonate. So they will form salt. So the salt will be calcium nitrate. Calcium nitrate. How we know the salt is calcium nitrate? You take the positive ion combine with the negative ion. Okay, so then you get the salt. Then carbon dioxide. Carbon dioxide is from here. CO3 becomes CO2. And then after that, form water also, H2O. So we balance it with times 2. Okay, so with times 2, we have 2 nitrate and 2 hydrogen combined with 1 oxygen. So the equation is balanced. Okay, so you have 3 reactions for acid here. So you will see that the first reaction form gas. The third reaction also form gas. So strong acids completely ionize in water, producing lots of H plus ions. So what are strong acids? So normally you have to remember 3 examples. Strong acids are HCl, HNO3, and H2SO4. Hydrochloric acid, nitrochloric acid, and sulfuric acid. So if they are strong acid, they will 100% ionize to H plus. So when you draw the equation, when you write the equation, we draw this kind of arrow, irreversible arrow. That means they will 100% change to product and we don't reverse. Cl minus, NO3 minus, and SO4 minus, 2 minus. Okay, so this one we have 2 plus here. So from here, what we have to remember is completely ionized. Okay? Whereas weak acid is partially ionized in water, producing low concentration of H plus ion. So weak acid, other than these 3, you can assume the rest are weak acid. For example, CH3, COOH is a famous weak acid. This is called ethanoic acid. So when they dissolve in water, right, we have to use reversible arrow because they don't 100% change to product. So CH3, COO minus plus H plus. So weak acid, we use reversible reaction. So showing that not 100% of the molecule change to ions. Some remain as molecule. So that's why the concentration of H plus is low and hence the pH is higher. Maybe the pH is around 6 or 5. Okay, now we look at here. Properties of bases. Okay, so bases are insoluble substances which neutralize acid to form a salt and water only and are proton acceptors. Okay, insoluble substances. So example for bases is like calcium oxide. So calcium oxide is a base. Calcium oxide is a base. Okay, so it react with acid. So for example, it react with HCl. So what they form? Salt and water. So what salt? Calcium chloride. And water? H2O. Balance the equation, put 2 here. So the calcium oxide is the base. Base react with acid, form salt and water. Okay, so base are known as proton acceptor. Proton acceptor. So you want to see it, maybe it is not that clear over here where the base is the proton acceptor. You can't see clearly. I give you another example. Okay, so another example, ammonia. Ammonia. Ammonia is also a base. Okay, a base. You may feel like ammonia is a base, but they say base is insoluble substances. This is one aspect. Okay, base is insoluble substances, but
they actually mean by insoluble substance. Is it that it like cannot like dissolve fully?
yeah, cannot dissolve in water. Yeah. Okay, cannot dissolve in water. But if you read through more on base, you will realize that some books they say base is subdivided into 2 types. The first type is base that is insoluble, and alkaline which is soluble. Okay, so this point is at this stage the insoluble base. Okay, the soluble is known as alkaline. But when I say ammonia as a proton acceptor, I'm talking about this as the base. Okay, this one, the general name of base and alkaline. Ammonia is soluble actually. Okay, so we're supposed to call it alkaline. But when we come back to the general name for these two, it is also known as base. I'm talking about this base. Okay, so ammonia is a proton acceptor. Okay, so you react with H plus, react with acid, then the ammonia accept the protons. It shows that it's a proton acceptor. Okay, so alkalines. You see, in the southern they use alkalines. Alkalines is the soluble types of base. This base. I'm talking about this base. Okay, so the base itself has insoluble and soluble. Alkaline is the soluble type of base. So alkaline turns red litmus indicator paper or solutions to blue. So you have to remember, acid turns the litmus paper to red, blue to red, but alkaline turns the litmus paper from red to blue. Have pH 8 to 14. The pH 8 to 14, that means greater than 7. Okay, so 14 is a very strong alkaline, so 8 is the weak alkaline. So base plus acid becomes salt plus water. Okay, so this one we already have the discussion, which is so base plus acid becomes salt plus water plus CO2 when base is a metal carbonate. So from here we know that calcium carbonate plus acid become calcium nitrate, CO2 and H2O. They are talking about this metal carbonate, release CO2. Base plus ammonium salt, this is the second equation. Base plus ammonium salt becomes salt, ammonia gas plus water. So let's say example. Okay, so the base, let's say calcium hydroxide plus ammonium salt, ammonium chloride, let's say, becomes salt. So take the positive ion and the negative ion, calcium chloride plus ammonia gas, NH3 plus water, H2O. H2O, and we need to balance the equation. 2 oxygens, so I have to times 2 here. Now become 4 hydrogens, so I have to times 2 here. Okay, so then I have to times 2 here. Okay, it's balanced already. So that is the equation. Base plus ammonium salt becomes salt plus ammonia plus water. Okay, so yeah, strong alkalis completely ionized in water, producing lots of hydroxide ions. Strong alkaline. Strong alkalines, you have to remember. Strong alkalines are group 1, like NaOH, KOH, they are strong alkaline. Okay, strong alkaline. What else are strong? Strong base. Let's see some strong insoluble one. Strong base, you take group 2, the bottom one. Group 2 at the bottom, you look at periodic table, the one at the bottom is like barium, hydroxide, strong. Okay, so barium oxide. So these are the strong base. Weak alkalines, for example, ammonia. Ammonia is weak alkaline. So partially ionized in water, producing few and hydroxide ion. So let's compare between strong and weak. So for strong, you have to use irreversible arrow to form Na plus and OH minus. So meaning that a lot of hydroxide ion. Ammonia, we use reversible. We use reversible. So it's formed NH4 plus hydroxide. So when they react with water, then they will form this. Hydroxide ion is in low concentration. This one high concentration. 100% change to hydroxide, and 100. This one is just a little bit change to hydroxide. So if it has less hydroxide, weak acid. If it has high concentration of hydroxide, it is a if low concentration is weak alkaline, and if it has a high concentration of hydroxide, it's a strong alkaline. Okay, now we look at here. Neutral substances are pH 7. So for example, NaCl is neutral. NaCl is neutral. Okay. Acidity in soil. Plant grows at a pH near 7. If it is too acidic or alkaline, they will not grow. Acidic soil is fixed by adding lime. Okay, so you have to know lime in this particular way. So the lime here is not the lime which is the orange kind of lime. The lime here is the calcium oxide, calcium hydroxide. Okay, so you see some information about lime here. I let you look at the internet to take a quick look. Calcium oxide and calcium hydroxide. You can see here. The common names of calcium oxide and calcium hydroxide respectively are quicklime and stick lime. Okay, so they are lime. Is lime calcium oxide or calcium hydroxide? Both are lime, quick lime, stick lime, you know. So it's this kind of lime, quick lime and stick lime. Okay, so you add them to acidic soil, then they will neutralize the soil, and the soil become neutral. Okay, then you look at these neutrals, 7, pH 7. The universal indicator will show green. Okay, so these are the color of the universal indicator. Universal indicator is chemicals that can show color, and from the color you will know the pH. So if they show red, then that means the pH is 1. If they show purple or bluish, then it shows that it is alkaline. pH is the concentration of hydrogen ions per dm cube of solution. So concentration of H plus, okay, that is pH in general only, you know. So of course we have a formula to count the pH, so which is not concentration only. We have something else, but we don't want to care first. For our syllabus, we just care about pH is just concentration of H plus. Okay, so if the concentration is big, the concentration of H plus is big, then the pH will be very low. If the concentration of OH minus is high, then the pH is very big, showing that it's alkaline. So on this side, we have phenolphthalein. We call it indicator. So indicator is actually the chemicals that will change color in acid and alkaline. So phenolphthalein in acid, colorless; in alkaline, is pink. Okay, so methyl orange in acid is pink, in alkaline is yellow. Methyl red, red, yellow. Red litmus paper, red, blue. Blue litmus paper, red, blue. So this is the color of the indicator in different pH. Okay, so one more indicator which is not mentioned here is universal indicator, which show all kind of colors, okay, in different pH. Okay, now we have done acid and base, so we have to do some question first before we look at this page. This page is salt already, the starting of salt. We will look at this later. Okay, so we have so many tests over here. Okay, now let's see questions. Okay, sulfuric acid and malonic acid are both dibasic acids. The dibasic acid is one molecule of acid has 2 hydrogen ions that can dissolve in water. So form 2H plus. 1 mole of a dibasic acid can form 2 moles of hydrogen ions. So that explained to you. Then I give equation to make it clear. Dibasic acids can form salts of the type Na2X and calcium X. Okay, so the X here is having a charge of 2 minus, as if you can imagine. So this is X2 minus, X2 minus. So malonic acids is a white crystalline solid which is soluble in water. They purposely give you some unknown acids. I mean less famous acid. Okay, so and it melts at 135 degrees Celsius. The structural formula of malonic acid is given below. So this one, CH2, COOH2. That means COOH on both sides, CH2 in the middle. Okay, its form salts called malonate. How could you determine if a sample of malonic acid is pure? So to know whether it is pure or not, we have to check the melting point. Melting point. Okay, so this one, they give you the information. It melts at 135 degrees Celsius. You may heard of this in water. If the water is pure water, it boils at 100 degrees Celsius. If you have something in the water, like if you put salt or sugar in the water, then the boiling point is greater than 100. Okay, so it's something like that. So we use the same technique to answer this. We measure the melting point. We measure the melting point. Okay, so result is pure. Result is pure. That means pure acid, pure malonic acid would melt at 135 degrees Celsius. What is the molecular formula of malonic acid? So you have to take this and total up the carbon. You get 3 carbons, C3. And then you have to count the hydrogens, total up the hydrogen. You will get 2 from here, 2 from here, H4. And then you have 2 oxygen times 2 become 4 oxygen, so O4. Molecular formula is the total of each element here. Part 3, when malonic acid is heated, there are 2 products, carbon dioxide and a simpler carboxylic acid. Deduce the name and molecular formula of this acid. So you have to deduce the name. So you see from the formula, CH2COOH 2. Okay, so which is C3H4O4. If you minus away carbon dioxide, so you minus 1C minus 2O. So you should expect it is C2H4O2. C2H4O2. You have to deduce the name, the molecular formula. Molecular formula, you know already. C2H4O2. That's the second part of the question. How about the name? So you have to think about it. What kind of acid is this? So logically, you should be able to imagine. You look at this structure, right? If you cut away CO2, so what remains is CH3COOH.
Carboxylic acid. So can you hear me?
What you said again?
It's a carboxylic acid. It's a carboxylic acid, right?
They want the name, no?
Oh.
So what we say? Ethanoic acid, which is a carboxylic acid.
So ethanoic is a carboxylic acid, right, sir?
Yeah.
Okay.
Just that we want to specify it to the 2-carbon carboxylic acid.
Okay.
Ethanoic acid. They give you hints here, simpler carboxylic acid. So what is the name of that carboxylic acid? Ethanoic acid. Okay. Now we look at part 4.
So.
Yes.
So when they say deduce the name and molecular formula of this acid, so deduce means what actually? Because in Form 6 for chemistry I gone through this kind of questions, but then the answers are totally different. So can you explain to me, if whenever I see deduce, what should I do?
Nothing special actually. when they say deduce, you just use the previous result to work out this question. Use previous result to work out this question. That is deduce. Okay, so previous result, for example, you have to make use of your C3H4O4. You have to make use of the information given to think about it. That is the meaning of deduce. There is a specific definition for deduce, but no need to know one actually. Okay, so in general, just use the previous result to work it out. That is deduce. Okay, so there's a specific meaning like, from something specific, find out something general, who want to care about that, so no need to care about that, no need to go until that extent. Okay, so part 4, malonic acids react with ethanol to form a colorless liquid which has a fruity smell. Fruity smell is very important. Ester. Okay, ester, that means it is ester. Its structural formula is given below. So you can see this is the structure. COO is the functional group for the ester. What type of compound contains the group which is circle?
Ester.
So ester. Okay. Ester has COO. Ester. Okay. Then of course, you may wondering ester. Never heard of ester? You will learn later under organic chemistry. Okay, so we look at B, part 1. Suggest why a solution of malonic acid concentration 0.2 mole per dm³ has a higher pH than one of sulfuric acid of the same concentration. So basically because it is a weak acid. So we write down malonic acid is a weaker acid. Okay. Now describe a test other than measuring pH, which can be carried out on both acid solutions to confirm the explanations given in B1 for the different pH values of the two acids. So if they have strong acid and weak acid, what kind of test can we perform? Okay.
So
Yeah.
I'm a bit confused in B1 when they say that they are mentioning in B1 that the malonic acid has a higher pH compared to one sulfuric acid.
Okay.
So so if something has a greater pH, that means its number of hydrogen ions is less.
Yes, correct.
Okay, sir.
Yeah, that's hydrogen ion and it's a weaker acid. Yeah. Okay, so now we have to describe a test. So there are many ways to test it. So one of the way is you just add reactive metal like magnesium. Okay, then after that, how to see the results? You will see the sulfuric acid react faster. You can also write malonic acid reacts slower, so you just need to compare. So you can also write malonic acid reacts slower. So we just said it in general. Then you look at C. Complete the following equation for reactions of these two acids. Sodium hydroxide plus malonic acid, and they want words equation. So it should become sodium malonate. Malonate. You have to get used to the change of the name here. Okay, like carbonic acid, carbonate, ATE. Okay, sulfuric acid, ric become ate, become something sulfate, become sulfuric, sulfate. Ric become ate. So here likewise, Nick become 8. So IC become ATE lah. So that is what am I trying to say. Water. Okay, now we look at part 2. So for part 2, you can see something like chemical formula is used now. Copper 2 oxide plus sulfuric acid. So base plus acid becomes salt and water. So the salt should be
Copper sulfate.
Copper sulfate.
And water.
Okay, correct. Magnesium plus malonic acid. So magnesium plus malonic acid. So reactive metal plus acid should become salt and hydrogen gas, if you still remember the notes. So the salt, okay, CH2 COO 2 loses 2 hydrogens from here. So it becomes an anion with negative charge. So then magnesium will come there to form the salt, and then hydrogen gas H2. Carbonate plus carbonate, metal carbonate plus acid should become salt, CO2, and water. So the salt should be potassium sulfate. So K2SO4. Okay. Carbon dioxide and water. Okay. Then we check whether it's balanced or not. Yeah, it's already balanced. So that is how the question asks. You will realize the note is not so deep, but the question is deeper. Okay, they ask until the extension kind of question. Extension, not the basic question. You can see that. Okay, now let's continue with the notes. Okay, so we look at the second page of this note. Types of oxides. Metal oxides are basic. Example, iron oxide and magnesium oxide. Okay, general statement only lah. Okay, so if you sit down and think, you may think, oh, I know some metal oxide which is acidic. So that is that's why I say this is general statement. Okay, non-metal oxides are acidic. Non-metal oxides are acidic. So for example, sulfur oxide and carbon dioxide. You see, sulfur is non-metal, carbon is also non-metal. So when they form oxides, they form acidic oxides. Okay, so that means oxides can be basic, can be acidic. Aluminium, zinc, and lead form amphoteric oxides. Amphoteric oxide is the one that can react with acid, can react with base. So example, zinc oxides. So oxide which are neither acidic or basic are neutral. Example, water. Water is oxide also, H2O. The oxygen is there, which is oxide there. Carbon monoxide. So in conclusion, we have acidic, we have basic, we have amphoteric, and we have neutral. So we have 4 kinds of oxides. Okay, so why they want to talk about oxide? Because when we learn base, right? So we used to take oxide as our example, but be careful, not always. I mean, oxide is not always base, so it depends on what kind of oxide are we talking about. Certain oxide is acidic, certain oxide is base, certain oxide is amphoteric, certain oxides are neutral. Okay, so that clarify here already. Now, preparations of salt. You get salt when you take acid react with base, take acid react with metal carbonate, take acid react with reactive metal, you get salt. Okay, now what we want to know about preparation of salt is here. A salt is a substance formed when all the replaceable hydrogen ions of an acid are replaced by metal ions or the ammonium ions. So then it becomes salt. Okay, so salt can either be soluble or insoluble. Okay, so let's say I give you example of salt. So when we talk about salt, you must think of it come from what acid. If you can't think of what acid they come from, then it's not salt. Okay, for example, the type of salt here is sulfate, like sodium sulfate, potassium sulfate, zinc sulfate, calcium sulfate. So the sulfate come from sulfuric acid. So this is a salt because you can think of the corresponding acid, sulfuric acid. Nitrate, like sodium nitrate, is a salt because the nitrate come from nitric acid. You must think of the corresponding acid that form this salt. Okay. Then chloride. Chloride, sodium chloride come from where? Come from hydrochloric acid. Ethanoate. So, for example, sodium ethanoate come from where? Come from ethanoic acid. Okay, so maybe you feel like, can oxides consider a salt? No, cannot. We don't have any acids that form oxides. No, okay. So we can't think of any acid that form the corresponding anions. Then you don't call it salt. Okay, you can just call it ionic compound, for example, or other covalent compound. Okay, covalent compound, covalent molecule, or ionic compound. You can't call it salt. You must think of the corresponding acids in order to be salt. Okay, now we have two types of salt: soluble, insoluble. Soluble salt. Okay, let's see. All sodium, potassium, and ammonium salt are soluble. So we call it sodium, potassium, ammonium, which is SPA. All nitrate, soluble. Chlorides are soluble salt, except silver. Silver chloride is insoluble. Okay, and lead 2 chloride is also insoluble. So that means we have AgCl, which is insoluble, and PbCl2, which is also insoluble. Sulfates are soluble, except barium sulfate, lead 2 sulfate, and calcium sulfate. Okay, then potassium, sodium, and ammonium carbonate are soluble. The SPA carbonates are soluble, Other than that, the rest are not soluble. Okay, so to remember that. And now we look at here, starting with a metal. Add excess metal to an acid. Metal M. Add excess metal to an acid. When bubbling stops, the reaction is done. Okay. Filter off excess metal. So filter off excess metal. This is how we check whether the reaction, this is reactions involve acid and reactive metal. Which will form salt and hydrogen gas. Okay, and when the salts are formed, the reactive metal is used in excess, so that's why excess metal is there. So that's why you need to filter off the excess metal in order to get the salt. Okay, hydrogen gas is okay. Hydrogen gas, you just form bubbles and we just go to the surrounding on its own. But the reactive metal, the excess metal, will remain in the solution. So you need to filter it in order to get the salt. Okay, so now we look at the next one. Starting with an insoluble base. How we get the salt. Okay, so add insoluble base to acid and heat gently. It will dissolve. Keep adding until no more dissolve. So you keep adding acid. Keep adding acid. No more dissolve. Reaction is done. Filter out the insoluble or the excess base. Filter out, then you get the salt. Starting with an alkaline. Titration. Yeah, you see, put a certain amount of alkaline in a flask, add phenolphthalein, add acids from a burette, stirring until it goes colorless. Okay, from purple, when you add phenolphthalein to alkaline, it's purple or pink color. So then you add acid from the burette, then it becomes colorless. Find out how much acid you use, and then now you repeat without the indicator, that means without phenolphthalein. Okay, so then it will be more accurate. We don't want phenolphthalein there, and then it will be more accurate, and then you evaporate water from the neutral solution. Alkaline plus acid becomes salt and water, right? So you remove the water by heating it until it's concentrated. Then after that, you can get the salt. Then precipitation. Mix the two soluble salts so they react together. Filter the mixtures to separate the product produced. Soluble and insoluble salt produced. So you filter here. Paper 6, this one. You feel like, oh, all these are experiment types of information. So at the end, you should know that it will lead you to answering paper 6 questions. Okay, so you filtered it. The residue here is the insoluble salt. The filtrate here is the soluble salt. Okay, so this is this reaction is called double decomposition reaction. I give you one example. Let's say 2 soluble salt. You know, nitrate always soluble. Okay, so you use this table to help. Nitrate always soluble. And let's say I want to form an insoluble salt, which is lead 2 chloride. Lead 2 chloride. So I want to form PbCl2. So I'm going to combine my Pb with NO3. And I know nitrate is always soluble, so this is soluble. And I'm going to look at my Cl, so I have to think of a soluble salt. Okay, let's say NaCl. You know, SPA, right? SPA is soluble. So soluble salt mixed together, then they will form this. This is insoluble. PbCl2 is insoluble. NaNO3 is another product which is soluble. Then we balance the equation. So we put 2 here, put 2 here. Okay, the equation is balanced. So this is soluble. This is insoluble. Then you filter it. Then the PbCl2 will remain here. The NaNO3 will go down to the bottom. So that is precipitation method. Okay, now you see this. Important or not? Very important. Must memorize everything as clear as possible. Okay, so test for aqueous cations. So that means you have an unknown cation, you want to test it, so you have to do the following. So if the cation is aluminium 3 plus, it will show the following observation. You add NaOH to the unknown cations. If you get white soluble precipitate form, giving a colorless solution. So if this is the observation, okay, so then it is confirmed that the cation is aluminium ion. So what happened here is, you see white soluble precipitates form giving a colorless solution. So it means precipitate give colorless solution. That means actually there are 2 steps. There are 2 steps. First, you add a little bit of sodium hydroxide, it forms white precipitate. Then you add sodium hydroxide in excess, then the white precipitate dissolve in the solution to form colorless solution. And then if this is the observation, then it is the cation is aluminium 3 plus. So you see, oh, become very deep already now. The chemistry become very deep. Okay, so but if you add aqueous ammonia, same situation. First you add a little bit, they form white precipitate. Then you add a lot, the white precipitate remain as precipitate. It doesn't dissolve, So then that is the observation for this cation. Okay, whereas ammonium, you add alkaline. So you're supposed to remember ammonium salt plus alkali become salt, become ammonia, become water. So that's why ammonia gas is formed here. Ammonia gas is produced. It turns the damp litmus paper to blue color. Okay, so this is the observation. Calcium, if the cation is calcium 2 plus, so what happened is white precipitates form. So try to understand it in this way. You add a little bit of NaOH, white precipitate form. If you add sodium hydroxide in excess, the white precipitate remain as precipitate. Not like this, the white precipitate dissolve when you put in excess. So copper, okay, we see this first. For ammonia, no precipitate or slight white precipitate. So these two situations, either you don't see the precipitate or you just see a little bit of precipitate, and then it's calcium. Okay. Copper 2 ions, you add a little bit of sodium hydroxide, they form light blue precipitate. Then you add in excess, it still remain as precipitate. Whereas for ammonia, light blue soluble precipitate form, giving dark blue solution. That means when you add a little bit, they are light blue precipitate. If you add a lot, the precipitate dissolve to form dark blue solution. So that's how we take it. Iron 2 ions, green precipitate form. You add a lot of NaOH, the green precipitate remain. This one same also. You add a little bit of ammonia, they form precipitate. If you add a lot, the green precipitate remain. Iron 3, red-brown precipitate. Same with just now. Add a little bit, they form precipitate. Add a lot of NaOH, it remains as precipitate. So this one also similar for ammonia. For zinc, white soluble precipitate form giving a colorless solution. So this seems to be same result with aluminum. You add a little bit, they form precipitate. If you add a lot, then the precipitate dissolve. So we have aluminum and zinc with the same result. Then how to differentiate? You have to do second stage. Use ammonia. If you use ammonia, this form white precipitate, but this one form white soluble precipitate. That means you add a little bit, they form precipitate. You add in excess, then they dissolve. So aluminum and zinc, you can clarify or you can identify it by using sodium hydroxide followed by ammonia. Okay, so we always need to refer back to this table, when we do questions, especially paper 6. Okay, so we will refer back later when we do questions. And now we look at anion test. Carbonate, add dilute nitric acid. Okay, so you should expect if you add dilute nitric acid, carbon dioxide will come out. The carbon dioxide bubble gas. So you want to identify carbon dioxide, you pass through lime water. So you feel like, lime water, lime again. Is it the orange plus water? So it's not that kind of lime water. The lime water here is the calcium hydroxide here. So you see, all the slake lime, quick lime, lime water, they are all come from calcium. So pass through the lime water will turn cloudy. So turns cloudy. Calcium hydroxide will change to calcium oxide, which is the cloudy. Okay, now chloride, add nitric acid, then aqueous silver nitrate. So silver and chloride form silver chloride. Silver chloride is the insoluble salt, which is why we have this observation, white precipitate form, which is silver chloride. Silver chloride. Okay, so we add nitric acid for what? You just want silver chloride to combine to form AgCl. So we add nitric acid to purify it, to remove impurity. Okay, so bromide, bromide. Add nitric acid, then aqueous silver nitrate. So it seems like this one same test with the previous one. Yes, it's true for these three halides. These are the group 7 halides that do the same test. So we have silver chloride, which is white, silver bromide, which is cream precipitate, like the ice cream, vanilla ice cream color. Yellow precipitate is silver iodide. Okay. Nitrate, add aqueous sodium hydroxide, then add aluminium. So what happens is gas produced turns damp red litmus paper blue. Okay, so let's see what kind of gas is produced that turn red litmus paper blue here. Okay, so let me find out some informations from the internet. Okay, so let's see. Anion test for nitrate. Let me see the note first. Yeah, anion test for nitrate. Okay. Nitrate ion can be detected by reducing them to ammonia. Okay, no wonder. This is done by adding sodium hydroxide solution, then aluminum powder or foil. Heating strongly, ammonia is formed. Okay, so that's why the litmus paper is used here. Okay, so let's come back to the note. Okay, the red litmus paper turned blue because of the formation of ammonia. So ammonia gas is produced. Okay, now this one, sulfate. Add dilute nitric acid, then add aqueous barium nitrate. So nitric acid to remove the impurity, then you add barium nitrate. The barium will combine with the sulfate to form barium sulfate. So barium sulfate, which is the white precipitate here. So you need to roughly know why the test result is like that. Okay. This one I forgot to write. This is because of the carbon dioxide. Okay. Test for gases, ammonia. So for ammonia, what happened is this one. This is the ammonia observation, right? Damp red litmus paper turns blue. Carbon dioxide, lime water, bubble gas through lime water, and the lime water from colorless to cloudy. Chlorine breaches the red or the blue litmus paper. So that means if you're using blue litmus paper, for example, if you change it to red first, sorry?
It becomes white?
Yeah, it becomes white. Yeah. So what am I trying to say just now is the blue litmus paper will turn red followed by white. So it shows some acidic properties first, then because of breaching, it turns to white afterwards. Then hydrogens, place lighted splint, squeaky pop. A pop sound is heard. Okay, so what happens is hydrogen react with oxygen. Then there is a pop sound. So oxygen place growing splint, the splint relight. Okay, so that means it promote burning, So that's why you have this result. Okay, so we finished the theory already. Now we have to practice. And 3 will be suitable. Okay, so this question 3, let us see. Silver 1 chromate 6 is an insoluble salt. This is the formula. Silver 1 chromate 6. Insoluble. That's why you see they put solid there. It is prepared by precipitation. You know, you want to get a insoluble salt. You use 2 soluble salt mixed together, then they will form the insoluble salt. Okay, 20 cm³ of aqueous silver 1 nitrate. This one of the soluble salt must have the cation, another one must have the anion. Okay, so concentration 0.2 mole per dm³ was mixed with 20 cm³ of aqueous potassium chromate 6, which is this one. So the second soluble salt has the anion, the chromate 6. Concentration 0.1 mole per dm³. After stirring, the mixtures was filtered to get the silver 1 chromate 6. The precipitate was washed several times. That means you get the residue, then you wash it with distilled water. The precipitate was then left in a warm oven for several hours to remove the water. What difficulty arises if the name of a compound of a transition element does not include its oxidation state? For example, iron oxide. You see they put oxidation state silver 1. The oxidation number is positive 1. Chromate 6. The oxidation number is positive 6 for chromium. So if they don't put that in Roman, Roman numeral is used here, 1 and 4, right? So if they don't put, what problem? So we don't know whether they are iron 2 or iron 3. So we have this kind of problem. Okay, so we write down. Okay, iron oxide. If you don't put the Roman numeral, so what happens is iron forms Fe2 plus and Fe3 plus. So that's the problem. We don't know which one. Okay, so because they have more than one oxidation state. Okay, so because of that, the name should include the oxidation state in Roman numeral, something like here. So you should put it. If not, you will confuse. Is the iron 2 or iron 3? So B. These questions refer to the preparation of the salt. Why is it necessary to filter the mixtures after mixing and stirring? Okay, so preparation of salt. Why you need to filter? You filter to get this, to get this. Okay, so
Prevent impurities.
Pardon, you mean?
To prevent any impurities.
Prevent impurity. Oh, you can say to. You mean this one, is it? Is this the impurity that you mean?
Yeah.
Okay. And you can say to remove this one. Okay, filter to remove this or to get this. Depends on purpose. Okay, so if you say to remove impurity, then after all we
separate the silver from the solid from the aqueous solution.
separate them.
Yeah.
Our purpose is to prepare salt. To prepare salt. Okay, to prepare salt. That is our purpose. So that means we want to prepare this as our salt. So we don't want this, so we remove this. So we can say that to remove. You can write formula, or you just write the words to remove silver 1 chromate 6. What is the purpose of washing the precipitate? This one you can say what you will say just now, to remove the impurities. So yeah, the precipitate was washed several times with distilled water. Okay, so to remove the soluble is compulsory word. Without this word, you can't even get 1 mark. To remove soluble impurity. The soluble impurity will dissolve in water.
So soluble impurity is the potassium nitrate.
And so you have the extra potassium nitrate, you add water to wash it away.
Okay. Oh, from the filtrate itself, like we have to put more distilled water on the silver so that most of the potassium nitrate is washed into the conical flask. Something like that.
Ag2CrO4 is here.
Yeah, so they pour more distilled water on the on the paper to like on the filter paper so that the potassium will be most of the potassium will go inside the conical flask.
Yes. Right. And you wash it here, then KNO3 will go down. So, all right. Why leave the precipitate in a warm oven?
To get the powdered form.
Get what form?
To make it into a powder form.
Powder form. Oh, you mean from hydrated crystal form to powder form?
Yeah.
So let's just put in general to remove water. Okay, to remove water. Maybe you heard from somewhere from hydrated crystal to the powder form. Okay, so they just want in general. Explain why the concentration of silver 1 nitrate and potassium chromate 6 are different. So let's see, you see here 0.2, 0.1, different concentration. Okay, so of course you can see the ratio here is 2 react with 1, so that's why this one we need more, this one we need less. The reactions show that. Okay, so how to put in words? You just need to say 1 mole of this react with 2 mole of that. Okay, so so 1 mole of potassium chromate 6 react with 2 moles of silver 1 nitrate. Okay, what mass of silver 1 nitrate is needed to prepare 100 cm cube of silver 1 nitrate solution, concentration 0.2 mole per dm cube?
So,
Yeah.
For question C,
Okay.
you see that 1 mole of potassium chromate reacts with 2 moles of silver nitrate, which means, as the question says, like there is like 0.1 mole of potassium chromate reacting with
Yeah.
um, reacting with 0.2 moles of silver nitrate. So because of that, we have to put 1 mole and 2 moles, is it?
It's basically because of the equation here.
Okay.
The mole ratio is 2 to 1. So that's why the concentration of this must be double of this.
Okay, sir.
And now C part 2, it seems like they're asking for the mass. What mass of silver 1 nitrate? Silver 1 nitrate is this one. Is needed to prepare 100 cm cube of silver 1 nitrate solution, concentration 0.2 mole per dm cube. Okay. The mass of 1 mole of silver nitrate is 170 gram. So that tests you a few formula here that tests you on concentration equal to mole over dm cube, mole over volume in dm cube, volume in dm cube. That tests you on mole equal to mass over molar mass. Okay, that tests you also on cm cube to dm cube is to divide by 1000. Okay. You can even use mole equal to mv over 1000. mv over 1000. So where m is the mole per dm cube. So you have a few options to use here. So these are the formula that are relevant to these questions. Okay, so you have to find out the mass. So the mass is x. We don't know the mass. Okay, we don't know the mass. We want to find it out. So you want to find the mass. You already have the molar mass, and now you are looking for the mole first. The mole. So we can use mole equal to mv over 1000 if you want. If you don't want, then you just use this formula. It's up to you. So the mv over 1000, if you want to use it, the volume is in cm cube. So I use that, let's say, mole equal to concentration times volume over 1000. Concentration 0.2, volume 100 cm cube. You divide by 1000 to change it to dm cube. So that means we are using concentration times volume in dm cube to get the mole. Concentration times volume in dm cube to get the mole. So we just use calculator to count this. 0.2 times 0.1, we get 0.02. So that's the mole. 0.02 is the mole. Okay, now we use the second formula, mass equal to mole times molar mass. So mass equal to mole, 0.02 mole. Okay, let me put the unit first. Mole times molar mass, 170. Okay, then you will get this time 170, 170, 3.4 gram. Okay, so this is the questions where we have to pay more attention. You see that mix everything together. That makes the sort, then that makes the calculation part also.
Okay, sir.
So part 3. You see, until up to this chapter, you feel like, oh, the question is quite difficult to do, you know. Okay, so
So the molar mass is 170 gram for silver nitrate, right?
Yeah, molar mass 170 gram. It's also known as mass of 1 mole. So this is molar mass. So part 3, what is the maximum mass of silver 1 chromate 6 which could be obtained from 20 cm cube of aqueous silver 1 nitrate concentration 0.2 mole per dm cube? They ask something complicated, but they guide you. You count this, take this, count this, then you get. So first, of course, you have to, you know, you have to look at the chemical equation at the same time. Okay. In order to find the, okay, let me zoom out a little bit. In order to find the mass of the silver chromate 6, which is this one, silver 1 chromate 6, we need to know the mole of silver 1 chromate 6. So I put in a flow chart. You want to find the mass of silver 2CrO4. What required beforehand is the mole of silver 2Cr2O4. So that later you can time molar mass. You want to know the mole of this, what you need beforehand is the mole of either this one or that one. So you need to know the mole of silver nitrate or the mole of K2CrO4, so that you can use mole ratio from the equation to get the mole of this. So the process is like that. Find the mole of this one, any of this, so that you can get the mole of this. When you get the mole of this, then you will get the mass of this. So the step is like that. So let's see what information is given here. They give us 20 cm cube silver 1 nitrate, concentration 0.2. So it seems like we can use this mole equal to mb over 1000 to find the mole of this one. Okay, so we use mole equal to mv over 1000. So if you are not used to mole equal to mv 1000, you just take mole equal to concentration times volume in dm cube. So either this formula or this formula, depends on which one you are used to it. So we take the 0.2, multiply with the 20, but the 20 had to divide by 1000 to change from cm cube to dm cube. So that's why we have this mb over 1000. Okay, so at the end, let me write down the working. 0.2, the concentration, multiply with 20 over 1000, and then you will get 0.004. 0.004 mole. Okay, that's the first steps. So we have done this. Mole ratio from equation. You see the equation is ratio 2 to ratio 1. 2 to 1. So if you get 0.004 for this one should be divided by 2. So 0.002. Okay, you divide the first answer by 2 because of the equation. So 0.002 mole. Okay, I put the reason here. Because of the mole ratio from equation. Okay, you have the mole of this. Now you time molar mass, then you get the mass of that. So that's why the working is 0.002 times 332. Then you get 0.664 gram. So we get the mass. The chart is this one. You just follow this, and you will get the answer. Okay, so we have done these questions. So this is one complete question. Talk about salt in deep. Okay. Okay. So this is the whole questions, which is very related to what we learned just now. Okay, so we go through these questions. Calcium carbonate react with dilute hydrochloric acid. Okay, so just for practice purpose, we write down the chemical equation for this first. Calcium carbonate react with HCl. So we should expect it to form salt, calcium chloride plus carbon dioxide plus water. So we should expect something like this. Okay, then let's continue. We balance the equation 2, and then, okay, it's already balanced. Okay, now let's continue. The products of the reactions are aqueous calcium chloride. Okay, this one, aqueous calcium chloride, showing that this is soluble salt. And after that, water and carbon dioxide gas. A student investigated the rates of the reactions between calcium carbonate and dilute hydrochloric acid using the apparatus shown. The mass of the flask and contents were recorded every 30 seconds. When the reaction stopped, there were still small pieces of calcium carbonate in the flask. State what happens to the reading on the balance as the reaction takes place. Explain your answer. So the reading should be getting smaller and smaller, right? Should decrease because some of the products become gas and go away, and you can't avoid that. So that's why it's getting lighter. So reading on balance should decrease. Explanation: carbon dioxide. Carbon dioxide escapes. Okay. There is a piece of cotton wool in the neck of the flask. Suggests why a bung is not used in the neck of the flask. Okay, so why you don't use a bung to block the gas, but you want to let it go away. You want to let the carbon dioxide to go away.
Bounce.
It's like a cord, cord.
Oh. It's like the stopper.
The stopper. So they like to use different term a little bit from what we used to it. Okay, so it's a stopper. Okay, so the reason is why you don't use a bung. So because carbon dioxide cannot escape. Carbon dioxide cannot escape. If carbon dioxide cannot escape, then you will not have any change in the mass. Then you will see the same reading. Then how are you going to count the rate of reaction afterwards? So that's why we have to use a cotton wool. So that's why cotton wool is placed in the neck of the flask rather than leaving the flask open. Why we just leave it? Why we don't just leave it open but use a cotton wool? Okay, so is to prevent acid spray. To prevent acid spray. So that means when you add acid to calcium carbonate, so we afraid the acid to go away, so come up because of too reactive. So we don't want to have that. State which reactant is in excess. So the note here tell us still there were still small pieces of calcium carbonate. So they tell us. Okay, so calcium carbonate. Calcium carbonate. Describe how crystal of calcium chloride can be obtained from the mixtures left in the flask after the reaction has stopped. So you have to know that the calcium chloride is the soluble salt. So first you have to filter to remove the calcium carbonate in excess. To remove calcium carbonate. Calcium carbonate is the insoluble substance. Then you have to heat to evaporate water. Then you have to heat until saturated. And leave to cool. Then the crystal is formed. So these are the steps that you need to memorize. Crystallization. Okay, so I think should be enough for now.